Hello everyone, welcome to this video class, and in this opportunity we're going to be talking about linked lists. So at this point we are probably familiar with the idea of a list or an array list, but I'm just going to do a quick reminder. So a list would be an object or a type of object that will allow me to hold data inside it. A typical example of a list would be the array list. And the array list has been proven to be very, very useful for several reasons, but one of them is that the size of the list, as opposed to an array, is flexible. I can add more elements to them or remove them, and the size will always change. Now, some of the methods that I have in the list, we're all already familiar with them. So would be, for example, the size would allow me to know how many elements I have in the list, whether it is empty or not, or if I want to get an element from the list given an index, if I want to replace an element at a given position, or if I want to add an element, or if I want to remove an element. So these would be some of the methods that a regular list will have. Now, the array list, which is the one that probably we've been using the most, is a data structure that holds some data, that holds some objects, but it is called array list because in the background, as an underlying structure, it is working with an array. So I just want to start very quickly, more or less trying to understand how an array list is working. So I would have, for example, let me just put here my pointer. So we have, for example, a array with an X amount of elements. Now, that doesn't necessarily mean that is the number of elements I have in the list, but it's just the capacity that the list has. So if I start adding the elements of the list in the array, so the list should be able to keep track of what is the last position that has been used and how many positions I have empty. Now, what happens, for example, if I insert an element in a particular position? So suppose this is my array and my list has this number of elements. It might not have the full array, the array completely full, but I have some elements in there. So if I want to add an element in position I, all of the rest of the elements has to be moved forward in a certain amount of numbers. And the same, so that way I can go and insert the new element into the particular position that I have defined. But the same thing happens when I'm removing. Suppose I have this element in here and I want to remove it because a list doesn't allow me to have gaps. Once I remove it is just not enough because that element would be, or that cell will be empty. So all the rest of the element has to be shuffled one position. Now, all of these procedures are quite costly and quite difficult to do. They're not terrible and you can code them, but that's something that you need to keep an eye. So another solution for a list that is not an array-based list would be a link structure. So when I have a link structure, instead of having an array as an underlying structure, what I would have is a bunch of objects that each one lives independently. And I can provide an order, but letting each object know who the next object in the list is. So a typical example of this is a treasure hunt. So if you're doing a treasure hunt, you get your first clue, and that takes you to the next element. And that element will give you another clue, and you go to the next element. And you go there, and that gives you another clue, and you go to the next one until you find the treasure. That is exactly the same principle that is applied for a linked structure. So all of the elements that are going to be part of my list will have a reference to the next element in the list. So normally, suppose you have, for example, a person object. Well, that person object will have a reference to another person object. And a series of person objects will make the actual list. So you have a reference to the first person in the list, and that first person gets you to the second to the third to the fourth, and so on, until you got to one element that doesn't have a reference to anyone, and because it doesn't have a reference to anyone, I can say, hey, this seems to be the last element in the list. So one of the things of the linked list is that they don't have any indexes. So they are really good because as there is no indexes, I don't need to shuffle people around when it comes to removing elements from the middle. We'll see in a second how we get that done. So first of all, the first thing that we're going to do is let's defining each one of the elements in the list. So suppose I have a list of strings, or suppose I have a list of person. So each element in the list will have two parts. The first part is going to be the element that is actually holding as part of the list, or as a part of the collection, and then the next part is going to be a reference to the next object. So that way, each element has always, at the very least, two parameters. So what I really need to make sure is that whoever element I have, I need to have a clear reference to who the first element is. So let's see, why are these structures so useful? Well, suppose, for example, you wanted to add a new element to the list. And remember, in a list, the order is important. Well, if you want to add a new element at the front of the list, this is actually very easily achievable. Because in the case of the array list, I need to put it in the first position, but whoever was in the first position has to go to the second, whoever was in the second goes to the third, whoever was in the third goes to the fourth, and so on. In this case, because I don't have indexes, I don't have to worry about that. All I need to do is I get my front reference and point it to the new element that I want to have, and I say to this new element to point to whoever was the first element before. So it's just a matter of changing the reference, and now the integrity of my list remains the same. So I have added a new element to the front without modifying the rest of the list, or without having to shuffle anybody around. But the same thing happens, for example, if I want to remove an object from the list. If I want to remove, for example, the first object, all I need to do is I need to change the pointer of the front and say, well, I don't want you to point to this object anymore. I want you to point to the object that continues. And all of these things are easily doable using Java. And being a little bit more generic, another thing that we can have with linked lists, and it really, really helps, is that you can have your data encapsulated in an object, and you can have another object called, for example, node, that will tell you who the next element is. Now, all of these things, I know it's very theoretical, but we're going to have a look at this in practice. So for example, this is exactly what I've just explained before. So for example, if I want to add a new element to the head, all I need to do is to move the pointer from the first element to the new first element, and just point that element here. If I want to insert somebody at the tail, exactly the same story. I have my tail pointing in here, and this one is pointing to null. So I just have a new element in there. I just get the tail pointing to the new element, and I get whatever was the last element before pointing to the new element now. Same story with removing from the head. So if I want to remove, all I need to move is the pointer that originally was pointing in here. So I just point it to the next element in the list, and this one disappears. And the same thing happens at the back. Now, what I want you to do is, to try to do now, and that would be in the next video, is to implement these principles using Java code. So I'll see you in the next video.